these data will be available via a recording as well. My name is Durrell Rittenberg. I'm the Director of Product Management for Tecplot, and let's go ahead and get started. So a couple of things that we've noticed over the last 24 months has been a marked increase in the number of CFD solutions that are being used for any one project. In effect, 10 years ago, really we didn't have the computational resources to run a lot of cases. As a result, most people were very judicious in how they used their computational resources. And there weren't that many solutions. In fact, for the most part, computational resources were being expended on higher resolution simulation. What we're finding is that with the new Intel chips and, of course, with the proliferation of low-cost computational resources, including the cloud, people are now trying to do some of the work that they would do perhaps in testing in simulation. And so we're looking at hundreds, thousands, and in rare cases, hundreds of thousands of high-fidelity simulation cases. And this poses a very different problem to what we've been dealing with in the past, because we grew up with a different paradigm, looking at one result and trying to apply those basic constructs to aggregates or ensembles of results is something that's somewhat new. And that's an area where we've been doing a fair amount of work to try to see if we can help make that process more facile. So in that context, there's really been two main applications of the simulation that we're speaking about today. The first is more production-level CFD. In production-level CFD, what we're seeing in the industry is primarily around performance prediction and or optimization. So in this context, a lot of people are actually trying to predict performance of a vehicle in advance of building it, with the idea of saving a lot of money as one can make some design decisions early on in the process, which have huge implications downstream when you start to think about the overall project costs. So in essence, what people are doing are looking at velocity spaces, configurational spaces, to get flight characteristics or to get performance characteristics of any type of vehicle, which is slightly different than perhaps exploratory CFD. Now, in the context of exploratory CFD, we're really looking at people who are trying to optimize conditions to get a very accurate solution. This could be anything from evaluating CFD codes, code parameters. We have seen a fair amount of people doing grid resolution studies as well. The big difference between the two is that in the context of exploratory CFD, although there are several results one might be looking at, you're really trying to do comparisons of accuracy around a given set of initial conditions, which is, or a smaller set of initial conditions perhaps, than what you might be doing in production level CFD. But the end result is you have tons and tons of data. What we want to help you do is pull out the data from all of the information that you have. It's really those needles within the haystack that help you understand how a system is performing. And that's really the goal of what we're going to talk about here this morning. We do have a reasonable number of people online, and what I would like is if you have a question that you want to answer, you can ask that directly in the question tab. So if you do have a question that comes up, I'll try to answer that. At the end of the presentation and demonstration, we'll have an opportunity. If you do have questions, you can raise your hand, and provided you're available via microphone, you can actually ask the question directly. Okay. So in the context of what we've been seeing over the last couple of years is that as an engineering community, we've certainly applied a number of disparate methodologies in order to try to analyze these aggregate results. And what we find is, for the most part, it's broken into between 4 to 7 tools. We have tools for physics visualization. This would be akin to what Tecplot 360 provides. We have analytical tools and scripts. These could be anything from doing integrations, integrated quantities, modeling, data reduction. We have a lot of people who do surrogate modeling. Not everyone does, but this could be something as simple as a response surface, and these can be done in a number of applications, including Tecplot 360, but MATLAB or any like tool. And then you have the ultimate ability to take that information, or really the task is to get that into a table or a set of values that you can send off to another group that might take those values and use them for the next step in the process. So this is kind of the way people are applying it today. We've been thinking there's got to be a better way. So we've developed an application called Tecplot Chorus. And Tecplot Chorus is a framework to manage CFD projects with multiple simulation runs, with tools to evaluate the resulting metadata, and I'll actually walk through this. But the three main components, physics visualization, analytics around metadata, and project management are really the cornerstone, so to speak, of what Tecplot Chorus provides. So really in the context of that's simulation analytics, which is the coupled analysis of detailed flow fields, and the associated metadata or integrated quantities and other descriptors. And those consist of anything from visualizations to data management, statistics, and data mining. We'll try to touch on each of these pieces as we go through. So the first thing we're going to talk about and actually demonstrate and walk through in our two use cases will be how to create projects directly from raw simulation results. We'll show you that it's very easy to bring that information together. And in our use case, we'll walk through one starting from raw results directly from a table, and the other will be actually from a set of directories where the data live. The thing we're going to show you is that once you are dealing with those aggregate solutions, those ensembles can be analyzed like they were one, but you can do that on 100. So that allows you to be much more productive, and I'll show you that it's relatively simplistic. You can actually go through and do that. And then finally, or probably most importantly, is comparing those results, both qualitatively and quantitatively, to understand effectively what the differences are. And you can see that ranges from doing simple visual comparisons to qualitative image differencing to ultimately looking at quantitative differences of the actual CFD solutions. We'll walk through a couple examples of that as well. At the end of the day, though, you want to tie back to the integrated quantities. Those integrated quantities typically are going to be around using surrogate models as well as response surfaces, and ultimately being able to take that information out into a table that then could be shared with an additional group. So basically what Chorus is going to provide, and I'll show you in this example, is the ability to tie together physics and integrated quantities into one environment so you can make a decision based on holistic information. And it's that ability to understand what's driving the physics that allows you to make a better decision. In effect, it's like having a hyperwall on your desktop. And for those of you, perhaps, I think we have a couple from NASA. In effect, Tecplot Chorus provides a mechanism to do much of the work you might do with a hyperwall like out at NASA Ames. And we'll show you that you can actually evaluate sets of results very quickly on your desktop. And our first use case is going to be looking at a low-resolution UAV performance prediction study. The primary thing we're going to be looking at here is to understand things like alpha max, and we're also going to be looking a little bit beyond its flight envelope. We're going to be looking at higher speeds than this particular vehicle will fly, but you can start to understand what the net impact of trying to fly at those higher speeds will do. So the background on this, we really are looking at high-fidelity simulation, although the resolution of this particular mesh was somewhat low. But using high-fidelity simulation to predict performance early in the design process has been shown to save quite a bit of money. So as organizations look to computational resources and mechanism to, in effect, drive some of their design work, they're trying to use these high-fidelity methods early in the design process. Now, as engineers, of course, we need to develop methodologies that the design team can use to test these potential character or configurations. So the tools and processes that we're trying to develop in this case are around how does one analyze a set of information to help understand and drive perhaps this performance. And this is one of the reasons why we've seen such an increase in the number of simulations in a given project, because people would like to be able to do some initial performance calculations prior to even making a final decision on design. So the data, as I'll show you very quickly, we're looking at about 34 cases, and each related to the UAV I show you here. I actually have it upside down, but I wanted to look a little bit more like the image. And what we'll be looking at are the integrated quantities, lift and drag, and we'll actually be trying to model the drag surface. So the summary, we're going to show how it's relatively simple. We're going to pull together the information into a project. We're going to analyze the results by creating a series of visualizations and other analytical strategies to evaluate system performance. And ultimately we're going to show you how easy it is to actually create a report. So we'll create a project, we'll develop some assets for comparison, identify key characteristics like alpha max, and then we're going to show how you can create a report. So let's go ahead and get started. And with that, I'm going to exit PowerPoint momentarily, and we're going to go into the actual use case. Now, some of you may have faster or slower bandwidth, so I don't know how quickly this is going to update, so I will try not to go too quickly. As I said, the recording of the actual use case for both of these will be available shortly after the webinar. You'll be able to go through then and take a look at each of these, and perhaps if you want to go in more detail, there's a little more detail in those workthroughs. So the example we're looking at here, you can see we're looking at Mach numbers that range from 0.4 to 0.8. And for each Mach number, we're looking at a series of alphas from alpha 0 to alpha 25. And within each alpha, we're looking at betas from 0 to 15. So it's not a true orthogonal array, but the basic concept is similar. And for each one of these, we have a volumetric solution, a relatively small volumetric solution in this case. The idea here is that for any one of these, one could access the data and analyze it using Tecplot 360 or physics visualization. And what we've seen in the industry, and for those of you who perhaps seen some things on Chorus before, is that for the most part, how people have been doing this is they'll analyze one, perhaps drop in a slice, look at the pressure, and one of the things that they'll try to do then is say, okay, well that's my basic view, and then they'll try to write a macro that effectively would do this, and either using a shell script or Python or some other scripting language, they'll then go through and try to create a series of standard images, and then those images are in a directory, and the idea is that they can go through now in that directory and look at the images. It's not a perfect process, and the link between the physics and the images that are created is often lost. And the other thing that doing it in that method that can really kind of lead to some issues around path and other dependencies, especially if you're running on a Linux system. If you don't have all the dependencies in your script taken care of, when you try to run it again, it may not work. And so we're trying to address how one can work in a smarter way with Tecplot Chorus. So let's take a look at this system, and we're going to start by creating a project. And the project that we're going to create here is going to be based on, let me just move this over. It's going to be based on the data we're showing you here just a second ago. And I'm going to create a simple file to put the information in, and we'll call this 22 here. Doesn't really matter. And the project is, we'll call it low-res UAV. And we're going to use a file crawl. And the file crawl, we're going to browse out to the directory. The directory is on my desktop, and it should be right there. And this is the same directory we're looking at. And the next thing we're going to try to do is identify those independent variables. Those are the initial conditions. You can see we have Mach, alpha, and beta. And I'll very quickly just pull that directly from the directory structure. Now, you don't have to do this, as I'll show you in use case 2. You can actually have a index file as well. So it really depends on kind of how you set up your project. Gotta make sure we spell that right. And then we'll take beta as well. Okay. So what it's done down here is basically identified that these are independent variables, Mach, alpha, and beta. We'll hit next. The next thing we're going to do is bring in the actual files, which they're all field data. They happen to be PLT files. They really don't have to be. They can really be anything that can be loaded in Tecplot 360. We have a mechanism to set up reading parameters so that you can load anything that you so choose. And we'll try to make this slightly more descriptive. So this is the 3D field data. We'll leave all this alone. They're all independent variables. So within one click, what Tecplot Chorus then does is pull the information together into a project. So what you're seeing here, we have 34 CFD results, each one of which has a data file, and you can open that data much the way we did a moment ago. And we'll bring in that raw data, and now we can operate on one as if we're operating on all of them. So as it loads in information, you can see that we have links back to the independent variables. And if we apply a simple style to this, perhaps adding a slice, let's see, why don't we put a slice close to the nose cone here. And we're looking at pressure on this slice right now, but if we decided that this was a view that was interesting to us for whatever reason, and perhaps we'll add some additional contour levels, we want to see that the pressure coming off the nose cone, we can then save this as a template. Now the great thing about this is we can call this nose pressure. And once we have access to this new template, if we go back into Tecplot Chorus and grab any one of these files or any one of these cases, we can hit a view data and take advantage of that new template, nose pressure, and hit OK. And what will happen is it will actually push that information over. So you can see that in this case we have a relatively high beta. We're at a beta 15. And that kind of bears itself out if you look at the pressures on the nose cone. If we go back to the original case, so you can actually pop back and forth, almost looking at it like two different slides in a PowerPoint deck. So it's a good way for us to start. We're starting to see how the system behaves. The next thing we want to do is we want to actually use that methodology to develop a set of assets that we can build into our project. So we're going to grab all of our results and we're going to create an asset, an image, based on that nose cone pressure, and we'll hit OK. And what Tecplot Chorus is going to do now, it's going to manage the batch creation of those, and looks like it didn't grab all of them, but that's not critical for this moment. Okay, as it's creating those images, we're going to go ahead and look at a few solutions side by side. So we want to look at, say, both the high alpha at 0.4 and 0.5, and actually, heck, we'll look at 0.6 as well. We're going to view those data. We'll use the same strategy by looking at the pressure coming off the nose cone. And now we're going to open up those three results in one environment because we'd like to do some comparisons. So I'll make this a little bigger for you. Okay. So what we have here then are three results, and they're all tied together. So if I rotate or zoom around, you can see kind of how the system is behaving. Maybe what we want to understand is the only thing that we've changed here, in addition to the alpha being constant, the beta is constant, so the Mach number is what's changing. So we'll understand what the net impact or what change you might see from going from Mach 0.4 to 0.6. So by grabbing one of these, I can actually show a difference. So now we're going to do a quantitative difference, and we're looking at now the delta in pressure in the bottom two between the base case or nominal case at 0.4, Mach 0.4, and 0.5 and 0.6. You can see that there's some fine structure. In essence, the differences are being washed out, perhaps by our contour levels. And we can add some additional contour levels that will help us identify that fine structure. And the great thing about this is that, again, without any real scripting, one can actually apply those styles across. So now we can start to get some idea of the quantitative information. Just looking at the deltas, we can start to see what that pressure difference is looking like. But at this point, we've really only talked about qualitative information, and we need to bring in some of the quantitative information or integrated quantities so we can understand system performance. So let's go back here, and you can see that the job is complete. We'll hit deposit. We're going to put that asset into our system, and if we go now and look at a quick view of the data, and this is a matrix view, what we're looking at now is for the different alpha, going from alpha 0 to 25, and we're also looking at Mach number from 0.4 to 0.8. And you can start to see what the net impact is of that change. Now, I only have one asset here. The last thing I'm going to do actually is append the data. I'm going to bring in the integrated quantities, and we'll just do that using a text file. And the data are on the desktop. You just need to browse to the text file in question. This can be kind of an index file in principle. And so let's just go in the right directory. And you'll see there's something called results. When we hit open here, and you'll see that it brought in some information. Oops, let me go back here. Sorry, wrong one. There we go. Okay. So in essence, there's one about the CFD code we'll bring in as code, and when I hit next, it's going to bring in the information, the integrated quantities for each one of the cases. And we'll go ahead and allow that to come in. And now if we go back to our spreadsheet, you'll see that our spreadsheet now includes integrated quantities. And we can start to evaluate those integrated quantities by looking at them as a 3D plot. So in essence, we're looking at drag here. This is the drag polar. and we're going to fit that using a simple surrogate model. Okay. Once we bring that in, we can show the surrogate model, and you can see what the fit looks like. Now, since we're using a simple quadratic response surface, we can get a basic sense of the overall fit by looking at the R-squared value, which in this case, the R-squared value is about 0.92, which is not great. If we wanted to improve the accuracy, we could limit this to just one beta value. So we'll go to a single value filter. And that should improve the fit nominally, and it did a little bit. There's also some points over here you can see that look to be unusual. We can quickly take a look at one of them, or look at them together. So we're going to view the images. Okay, so we're starting to understand why we might see this high drag. There's definitely a difference in pressure here. What we might want to do is see how different they are from a nominal case. So if we look at one of the more well-behaved cases, we can actually accumulate that across. So now we have those 3 images, or 4 images. And we can start to look at differences from the nominal case just by doing a difference. So this is a qualitative difference looking at the pixels, showing you that in fact you can look at a whole bunch of different views of the data that will help you get kind of a qualitative look at how things are changing. So it's very easy to do. Now there's a number of other images that I'd like to actually bring in. So what I would do effectively is come in here, grab all my cases, and I'm going to create some additional assets. Now, in the interest of time, I've already done that, and I will go ahead and open up a project that I've done some work on. And this is actually a very similar case. It's actually the same data, but I've actually run through a few more images. So let's start by looking at that same plot that we showed a moment ago, and we're going to quickly take a look at all the different assets we have available. And you can see that we can look at anything from cut at 80% of wingspan. We can look at the CP plots. So now we're looking at qualitative and quantitative information. We can look at a slice at 50% of wingspan. We can look at the pressure isosurfaces coming off the body. And we can start to walk through very quickly and see how the system is behaving. And one of the things to point out is, as you might expect, at the higher alpha values, we actually do have stall, and you can see the areas of recirculation here by looking at some stream traces coming off the wing. So it's a very easy way to try to identify. So it looks like in this case, although we didn't run any values between 15 and 25, by 25 you actually are past alpha max, and if you looked at the overall lift, it would go down significantly. Okay. So there's a couple questions about grid. There's 2 things to point out. That in this particular case, we use the same computational mesh. If we had a different mesh, Tecplot Chorus can certainly handle different meshes. When you do a quantitative delta, the data today needs to be the same mesh. We're working on some strategies to apply some interpolation methodologies that would allow you to do quantitative deltas based on different meshes. So there's been a couple questions on that. But as of today, you're really limited, at least initially, to the values or the meshes that are the same. So, okay, let's go back quickly. The other way that one can actually evaluate these data would be to evaluate multiple views of the data based purely on the case ID. So in this case, we're looking at a number of cases that we've selected, and we're looking at just some quantitative information. We're looking at 80%, 50% wingspan, as well as the pressure isosurface. And as we go to those higher alphas, in this case, we can actually turn on some labels to make this easier to see. What you'll notice is that as we go to those higher and higher Mach numbers, of course, this plane really does not fly at Mach 0.8. I think it would be very unstable, frankly. But the idea being that you can really start to understand how things are changing. And this whole concept of being able to look at multiple physical views and quantitative views of your data of each case is somewhat unique to Tecplot Chorus. And the fact is you just don't need to do scripting. You can kind of walk through this very simply. Similarly, if we go back to our matrix view, you're not limited to looking at independent variable space. You could actually look at tag space. So for example, if we chose to look at the net impact of alpha as a function of tag. So instead of looking at Mach here, we're going to use tag. And then we can actually walk through mock space. So as you can see here, we're looking at a number of tags, and we'll limit this to just enough on screen. So now we look at the tags, and we're going to walk through the mock numbers. So as we increase mock, you can see what the net impact is to the performance of the system. So it's a very easy way to evaluate performance or look at overall operating conditions very quickly. And it's an interesting thing that your eye kind of picks up some of the changes, like at the high alpha. When you go to about Mach 0.6, you'll see that you have this very discrete low pressure area. And in fact, if we look, you'll see there's that recirculation, so it's consistent. So this is a very simple way to evaluate system performance. In this particular case, we're using a UAV. Now, up to this point, though, what we've done, I think, is helpful. But if we were going to deliver to our customer what they need to be productive, so we're going to look at the overall drag. This is the surrogate model through drag of a subset of the data. And we may actually want to take these data out into a file. And we have an opportunity. We can actually use either quadratic response surface and or kriging. And we have the capability of taking this out in two ways. Now, one way, of course, if we just look at this as an image, I can just right-click, save this directly as a plot. And if I save it out as a plot, I can then bring it back into PowerPoint or what have you. So that's certainly one way to do it. The other thing, of course, is you can take a look at what values you want to use. So you can actually use a simple way to limit the data. So if we wanted to look at perhaps between 0 and 25, but perhaps we only want to go up as far as alpha 5. So you do have a way of, in effect, taking this information and really changing the view on screen, including everything from transparencies. You can also, of course, from a project, export this. You can export the data to a CSV file. I'm not going to do that here today, but you could then take that CSV file, which is basically just the fit information, and then give it to someone who might need to use those information as set points or start points for another analysis. Okay. The other thing we're going to look at is talking about how you might want to take these images. So one thing when you're doing a report like this, if you did want to look at these high Mach numbers at an alpha 0, you have the ability now to say, look at a set of images, say these 3 cases, and we can now export these images collectively. And if we say where we want to put them, I guess I'll put these on the desktop, or actually perhaps I can put it in temp. Let's just try that. I guess we need to have a directory there, but anyway, we can export these directly to the desktop. And what will happen is, if I go to my desktop now, as you'll see that we have all those images available, and there's just one of them here. Okay, and they actually include the tags, so it's quite nice if you want to bring these into PowerPoint. You can actually walk through each of the images that we have. So from a reporting standpoint, if we go back to this particular use case, we may actually want to bring out just a couple of these images, so you can actually select an image and copy it directly to the clipboard, which allows you to go back into PowerPoint, perhaps, generate a new slide, and we can go ahead and just drop in that image. We'll just make it a little easier to see. Okay, and we'll actually, let's try changing the layout here so that we just have a side-by-side comparison. And then we can grab a second image here. We'll go back to Chorus, perhaps of one that's doesn't show that delta in pressure. And now we can copy that directly to the clipboard and similarly drop that in. And it's a fascinating thing that PowerPoint behaves the way it does, but okay. And then, so you could imagine then bringing these into a group meeting, and if we quickly click on this, you'll see that now you can very quickly compare these results. So very, very easy to go from a project to taking those projects out and ultimately using them in a PowerPoint presentation or other report. And this is another area where we've seen a fair amount of interest, because it turns out that a lot of times when you have hundreds of solutions, it's not atypical to have one or two of them mislabeled, especially when you start to export images because the images look similar. By including the label information here, you can minimize the whoops factor when you're giving a presentation. So, okay. Are the export capabilities available in Linux? The answer is absolutely. This is not a Microsoft Windows only capability. I believe copy to clipboard, though, however, is a Windows only capability. Okay. And so very quickly, if we go back then, I showed you that we can very quickly create a project from raw CFD results. I showed you how to develop some assets for system comparison. We identified the alpha max characteristics by evaluating the overall off-wing pressures and looking for areas of recirculation. And finally, we brought that back into a report. And that's the basics of how one can actually use Tecplot Chorus with a set of solutions directly if they're in a directory structure that can be read in simply. Okay. For our second example, we're going to talk about a slightly different case where one of the key things that we're seeing out in the industry is there's a fair number of people looking at mechanisms for micropower generation. This is a big issue for people in countries where they don't have the infrastructure. There's really two main areas where people have invested a lot of energy. Certainly solar energy has been quite big. In fact, I was in Mongolia, which is east of China, northeast of China, and I was out almost an hour and a half away from anything, in the middle of nowhere, and someone living in a little gear had a big solar cell on top of their little yurt, and they were watching TV inside. So it's a kind of thing that, in the developing world, this is a real issue. So certainly solar power is quite convenient, but there's also a lot of people investing energy in wind power. And the idea is that people are looking for ways to use micro wind generators, and these are relatively small turbines, not like the ones you see when you're driving out in Idaho. So the idea was to see whether or not you could optimize performance of a system like this using optimization algorithms to maximize performance and really look for sensitivities. And then finally try to tie that sensitivity back to the physical behavior. How is this system behaving is directly related to how it was designed. You want to understand what's driving that optimization so that as an engineer you can say, okay, well that makes sense. And really, in the area of wind turbines, there's really two vertical axis wind turbines. There's Savonius wind turbines, which are more drag-based. You can think of these as almost like a scoop. You may have seen some of these before. The idea here being that they try to maximize drag. It produces relatively high torque, and so it's used a lot in things like grinding grain and/or pumping water. So that's one strategy. That's when we're talking about, we're looking for something that's a little bit different because we want high lift, high rotation for power generation. In this case, we're going to use the Darius turbine, which is a lift-driven rather than a drag-driven. And this is more or better suited to power generation than the Savonius wind turbine. So in this particular study, what we're going to look at is the results from the optimization, and we took 5 design points out for comparison. We want to evaluate the differences between the 5 design points and try to understand what are the physical drivers. So ideally, the goal of this particular study is to figure out of the 5 candidate designs coming from the optimization based on the constraints, which is ultimately going to give us the highest lift, or highest lift in this case, yes. And we want to quantify what the net improvement is. So the outline, we're going to show you that unlike the first project, we're actually going to use an index file, which includes both integrated quantities and, in this case, links to the actual data. These data were run in Fluent. One of the things that Fluent has, it does have some optimization algorithms built into Workbench 14. You can actually go through and do these type of work. We'll also show you, again, how to develop assets for comparison, and finally identify physical drivers that influence the optimization, and we'll try to bring that back in a report. So let's go ahead and take a look at this second use case. So for that, I will go back into Chorus. Now we'll go and we're going to create a new project, much the way we did before. And this project, oops, I guess it doesn't matter. Call this 3. And the project is wind turbine. And we're going to use a delineated file, which is kind of like an index file. In this case, it happens to be a text delineated file using commas, but it doesn't have to be. It can really be any delineator you want, from tab to space. And here the output total is just a simple CSV file. When we hit next, we just have to point it to the right area, which we're going to point it to the directory that holds the CFD data. Unlike the first one, there's actually a file to link to. So this is a file, and this is the file name. And this is, to be consistent with what we did last time, this is the 2D field data. And we'll also take advantage of the fact that time step, in this case, and the blade, which in this case is the blade generation, so we'll call this blade number, are independent variables. And in fact, when we looked at this system, those are the two things that we're looking at that are changing. This is the initial conditions. And this is the totals, and this is really for all blades. And that's what you're trying to optimize. These are the individual totals for each blade. So when I hit finish, what it does is it goes through and it's going to create a project based on the information that I gave it. Now, one thing to point out here is that you'll see that for the data themselves, if I hit view data, you have the 2D field data, nothing else. And there's a number of, in this case, pre-computed style files, but it's not important. And I'll just quickly open up one file so you can see what it looks like. So this is at a particular time step. And what we're going to be looking at is just a simple 2D cross-section of the airfoils. And if you zoom way in here, and so you can see this is the basic configuration. And what we'd probably be most interested in is looking at things like turbulence. So we'll go ahead and look at the turbulent viscosity, and we'll turn on the contour. So here's the basic view that we want to apply across all 55 solutions. So again, like the first one, you can actually set this as a template, and we'll call this T2 for simplicity. And we want to actually look at, because we're very interested in turbulence, especially around the leading edge, that might create additional drag. So once we have that template, we can go to any particular generation. So if I wanted to look at time step 0, for example, for all 5 blades, one can actually look at those collectively, and we'll look at the T2, and we'll bring those in. So now we're actually looking at all 5 of them, and you can see they come in very quickly because they're relatively small 2D data sets. And the idea is we're looking for differences, and you can see a very clear difference here, perhaps a little less so here. We may want to look at the time step and blade number. Now it's hard to see, so we may want to increase the font so that one can actually see what's going on. So okay, that looks big enough. And if I hit synchronize, it will actually just apply that style across. So it allows me to very quickly see, okay, understand those changes. Now you'll notice that you can't do a difference here because the grids aren't the same. You can do qualitative differences, and we'll show you that here in a second. So let's go back. I guess in principle we have an image we'd like to create now. So I'm going to create an asset or a set of assets based on my field data so we can start to look at additional analysis. So this is going to run in batch, and a couple things to point out is that Chorus allows you to run multiple batch extractions in parallel. Idea here being that we want to go through and parallelize the batch extraction, especially if you're looking at lots of data. Today that's limited to working on your particular workstation. The disadvantage of that, of course, is that if you have very large data, you probably don't want to do them all in parallel. You may want to do them serially. We have the configuration files available such that one can actually say, okay, well, I only want you to process one at a time. What I've noticed on my machine is anything over 100 million cells, and I'm running on a laptop, 100 million cells is really getting into what I'd say the limit of my machine or my resources are. On some of the workstations we have here, we've looked at data size on the order of about 1 billion cells. There was another capability about the, okay, well that's okay. Okay. So as you can see, as it's going through, it's going to process all 55 files, and that should take not much longer now as it's riding through. As I did with the last case, I am going to show you a couple of, I guess as they call it, the pie in the oven concept. We're actually going to take a look at a system that we've already done some of this work on. And so in the interest of time, and I want to make sure we have plenty of time for questions, I'll go back to my dashboard and I'm going to load in a session which I've actually done some of this work already. Okay, and it looks like the job's done, but we're not going to wait around for it. Okay, so what we're looking at here, in fact, is we're looking at blade generation versus time step. So you can see, in effect, here's each blade generation from 1 to 5, and we're looking at time going down the column or the row axis. We're going to shift that around. Let's actually look at blade generation versus time step. And then what we want to do is take a look quickly at perhaps the x velocity, or perhaps we want to look at the y velocity. And we want to take a look at the differences between the different blade generations. Now, I showed you that you can't do a quantitative delta, but you can do a qualitative delta. So I'll view these images now for all of the blade generations at that time step. And I guess in this case we'll show labels so that it's more clear. Really only care about those two. And perhaps we'll do the total as well. So this is the information that we're making decisions on. And what we want to be able to do is take the nominal case, which is blade generation 1, and compare it to each subsequent case. So if we do a difference now, you can see what the net differences are. And again, the key thing to point out here is that the key differences are actually in the area around the leading edge. And although you can't see that with the naked eye, in fact, if you do a pixel difference, you'll notice that in the blade generation 3, for example, you actually do see a little bit of that turbulence forming on the leading edge of the blade. And the idea is we want to actually move that turbulence back so we can maximize the lift of the system. So this gives us a very simple way to evaluate those differences. We can also evaluate looking at things like the vectors. Similarly, you can look at the x and y velocity, and you really have a lot of flexibility in terms of how one takes a look at the data that's shown on screen. Okay. So this is one mechanism, and this is an easy way to evaluate at any particular time step. Ultimately, though, you want to quantify those results so we can look at the integrated totals as a function of time for each blade generation. So you'll see here we have blade generation from 1 to 5, and what we're looking at basically are those integrated totals. In this case, a higher lower value is better. And what you find is that for the blade generation 4, there seems to be a significantly, it turns out to be close to a 30% improvement in performance. Now, if we wanted to, we can use filtering to walk through each one of these by going to a single value filter in blade generation, and now we can actually walk through each blade generation and see how the system is performance, or how is the performance is changing. So we're looking at now more quantitative and qualitative information simultaneously, and that helps us make better decisions. We'll go back to range filter. Now, if I had included more data points, in this case I brought in 5, but in principle the optimization ran through multiple generations. The thing about using these filters is one can actually look at each individual constraint and expand the constraint to see what the overall performance, how the performance changes. And then what we'll find, or what people have found, is that in principle when you start to do that, you start to understand whether or not a relaxing of a particular constraint might actually have an impact on the overall performance of the system. So it's a very interesting way to evaluate system performance. Another thing that's kind of nice to do is, instead of looking at time, in fact moving into these directories, you can see we actually have 11 time steps. One might actually want to look at this differently. Perhaps we look at blade generation again going down, and then instead of time step, let's look at tag, and we'll actually use time step as a mechanism to walk through the system. So here are the different tags, and now I can animate across all my time steps just by walking through time. So it's a very convenient way to evaluate how things are changing in time. And again, we're looking for this area in particular where you have that, from the nominal case, you see that we actually have some vortex shedding off the leading edge. And you can see that the optimal design actually moves that farther down the blade face and that leads to significantly higher performance for this system. Okay. So to go back, we talked about, in effect, looking at the data. Here are another mechanism. So this is the results again, blade generation on the x-axis versus time step. And what you can see that you can see the values of the overall performance on blade 1. But instead of blade 1, perhaps we should look at the overall blade total. And this is going to be akin to what I showed you in the XY line plot. Similarly, I can walk through each of these using my filter by looking at blade generation. And if we use a single value filter, you can actually look at each blade individually. And one could apply a simple surrogate model, and it's not going to be ideal given the low dimensionality of these data. But if we evaluated the surface, in effect, it's giving us close to an average. And we can go back and look at those averages, and you can see that for blade generation 1, 2, 3, and 4, it's not all that different, at least on the average here. If we go back to a range filter and go back to our line plot, we'll actually see that we can apply that same methodology and show the model settings as well. And you can see the overall improvements. So the last thing that I wanted to show you in this case, similar to what we did before, we have a mechanism where we can take this plot out, save it as a plot image, and we'll say this is a PNG directly onto the desktop. And we'll be able to take that information back into PowerPoint. So we'll pop in, grab a new slide. Same, we'll actually use a different layout where we can just look at two images side by side. We'll move this up just a bit. And we'll go ahead and paste that, or actually grab that image directly off the desktop here. So let's see if we can find that image I just created. There we go. So there's the quantitative information that I can bring in for my project. And the next thing I want to do is bring a representative image from the generation 4, which let's go ahead and make this bigger. So here's the 4th generation, and perhaps this is the most telling. So I'm going to view that image, and I'm going to copy that right onto the clipboard. And before I do that, actually, let me turn on the labels so we know what blade generation and then the totals are. And we'll show those. And then we'll copy that directly to the clipboard, and we'll go into PowerPoint now, and we can drop that image in. Okay. And we'll go back. So you can see it's very easy then to go from analysis of those results into quantifying the information necessary to make a decision, as well as take out representative plots that show, you can see we actually moved that turbulence off the leading edge. Okay, so that hopefully gives you an idea. We actually walked through 2 use cases, so just to go back to it, the idea here being that we wanted to use an index file to bring in and create a project, which we've done. We developed some assets for system comparisons. Those included images. We also looked at some of the integrated quantities as well. We identified the physical drivers, that was the drivers behind the overall improvement in performance. And finally, we created a report, brought that information directly into PowerPoint. And so we actually, as I showed you, we can create these kind of holistic views that help us make better decisions based on overall system information rather than point solution information. Okay. And this is an image. So parting thoughts. What I wanted to show you here this morning are some of the things that we've improved around Tecplot Chorus 2012 R2. The things that we were specifically looking at are giving you more unique ways to evaluate visually as well as quantitatively assets that are created as part of a project. Those include images, those include data files as well. This is the first application on the market that allows you to very quickly generate multiple views of aggregates or ensembles of CFD results. And that really gives you a better, in a way, it gives you a better framework to look at overall system changes and understand very quickly what, if anything, might be wrong with the system, although none of the data that I showed you here today did not converge, but there's plenty of times when you'll look at a system and go, well, that data didn't converge. In such a case, you can actually remove that from your project. One of the things that we're seeing, though, in terms of overall project setup and analysis, what used to take hours is taking minutes now based on this approach. Now, if you want to follow along on some of the things that we're doing before we open up to questions, you can join us either via Twitter, we're on YouTube, we're on LinkedIn and Facebook, and we have some ongoing discussions about simulation analytics and other applications of this methodology. And with that, I'm going to open it up to questions, and we have about 9 minutes, so you can do one of two things. Either you can raise your hand, so if you want to raise your hand, all you need to do is, well, I guess there's a little raise your hand thing. And what we'd like you to do is either raise your hand to ask a question, or, okay, there we go. Or you can just type the question in here. I'm trying to figure out how to, there we go. So either one will work for us. So if, let me see here, we have a couple questions that have come in. Oh, it looks like we have a couple people raise their hand, but they don't have a microphone, so maybe they'll have to type their question in. All right. Okay. There's a question around surrogate models. They say, okay, well, it looks like I only see Kriging and I guess quadratic response surfaces. And the question really is, can you use your own surrogate model? The short answer there is that we do currently have the capability internally to add additional surrogate models, and we're going to be exposing that to the outside in the next release of Chorus, which is due, I believe, sometime in September. Okay. Is our sampling method full factorial? In this particular case, it was not full factorial. We do have some people who are looking at full factorial results, but for the most part, we see most people doing either Latin hypercube, or there's been a fair amount of people who are looking at orthogonal arrays. But you're right. For Kriging, how much information you get back in the model. Right now, you can get back the surface from the Kriging. We're working on some strategies to give you some additional statistical relevance on your surrogate model. Working with a group out of University of Washington that will be helping us with a couple of those. So you don't get back an R-squared value because for Kriging it doesn't really make as much sense. But the idea here is that you can bring back some things like confidence interval. The other things you'll be able to look at is you'll be looking at, in effect, like box plots, where you'll get some statistical relevance of the data by looking at the quartile. So you'll be able to look at the second and third quartile as a band around the fit. So that'll give you some ideas of the fit in general. Okay, in that case, the matrix view may not work. Well, that's an interesting question, Jen. In fact, our matrix view right now will collapse. So if you were thinking of a Rubik's Cube, I think the question is that if you have a Latin hypercube, oftentimes you have a sampling of data through your space, so you don't have a full factorial of data to look down on in the matrix view, which is kind of akin to, I believe, what is shown, I think, in, let me actually just go back to that first case here. Okay, so the idea is that, well, you know, this is great if you happen to have data that just sit nicely in the different bins. One thing to point out, though, if I actually do none here, is that if there's additional data, and I guess I must have it filtered, there you go, you can see that it will collapse. So there's actually data behind this value. And if you look here, this is at an alpha of 0 and a Mach of 0.4, and you'll notice that there's these little icons. In effect, we collapse the information so you can see that in the matrix view, Jen. So even if your data is a Latin hypercube, you still can see it. The other thing that you can do that is kind of convenient would be to use the tag concept or case ID. So in principle, like you show here, this is actually case ID, which of the 35 cases you can see here. And one of the things that you can take advantage of is you can use a slider to do kind of a single value filter, and then you can see those. In this case, I don't have all my cases selected, but in principle, you can use that to walk through as well. So, good question, but yeah, you can definitely address it in in that way. Okay, there was a question about running additional results. As of today, the way that Chorus is set up, we are building the ability to run additional algorithms or anything outside. So it's kind of almost an API that allows a user to select information from here and right-click, and instead of it coming up and asking, do you want to export the images, for example, it would say perhaps create additional cases or rerun case, and you can kind of register your own custom actions, anything from running additional CFD runs to launching additional applications for qualitative or quantitative analysis to launching pair review or anything else you might want to launch directly from this interface. We have time for perhaps one or two more questions. The license term for Chorus, a very good question. The license term today, Jen asked, is you can have an annual license as well as a perpetual license. And the pricing information, I believe, is on our website, but it's about twice what Tecplot 360 costs, and it does include a version of Tecplot 360. It'll always be up to date. For the academic sector, it's significantly less expensive. Obviously, it's about 20% more than a usual license, so just shy of $1,000, I think. And we have time for one more question. Okay. Well, great. Again, I wanted to thank all of you for attending this morning. Hopefully, you got an idea of how Tecplot Chorus can be used on both optimization studies as well as looking at performance prediction. The information and the recording will be available by this afternoon, and we really appreciate you sitting in. Our next webinar will likely be a joint webinar between us and one of the people who've done a case study with either Tecplot Chorus or 360, and expect to see that in late July. I want to thank everyone for sitting in this morning, and we'll be talking to you at the next webinar. Thank you very much.